Hi everybody. So today we're going to talk about implicit differentiation. What is implicit differentiation? It's another technique that we're going to use to take derivatives. Okay. So you should be able to use that implicit differentiation, and you should know the difference between there, and there. It doesn't have the same impact second time around. Okay. So and we just lost somebody. This is great. Welcome to Monday, but it's Tuesday. Okay, so let's skip the technique and let's go to the function here. It's not even a function, it's an equation. You'll notice that I've got some y cubed, some y squareds, all this other business. If I had given you a function like this, okay, and I asked you to take the derivative of that lovely line in, what is that, general form, how would you do it, Bella? What's a derivative of that thing? How would you do it?
I guess I would probably put it into other notation first. I would solve for.
Perfect. Couldn't have said it better. You would solve this in terms of y. And then you could do a variety of different things, but take the derivative, right? So then we'd find y prime. Perfect. Now, what's the problem with this big scary thing up on top? Does anybody in this group know how to solve for y in that scary equation? No. The answer is no. I don't even know how to solve for y in that equation. So what implicit differentiation is going to allow us to do is take the derivative of equations where we can't solve for y. Okay? That's why we're doing it. Now, it goes like this. You're going to differentiate. What, Amanda just went and what the heck? Amanda just go take a.
Everyone's internet is really bad. I think that's why people are disconnecting and connecting again.
Okay. Amanda, you back? You good to go?
Yeah, I'm sorry.
Nothing to be sorry about. It's all right. You can't control that. Or can you? Okay. Differentiate both sides with respect to x. We'll cover what that means in a second. But you'll notice that in some of the notation we've talked about, we have a simple notation like y and y prime. But we also got into this notation. That was, I think that was Leibniz. I think Newton was the y prime, or f prime. Leibniz was this. That means a derivative of y with respect to x. So if we go back to the example that Bella had, once you solve for y, we would take the derivative of the function y with respect to x, which means that x is my variable. Okay. We're going to take the derivative of everything with respect to x. We're going to treat the y as a variable, and then when we're done, we're going to solve for dy dx. Now, to make our lives a little bit easier, we're actually going to replace the dy dx with y primes, because I have found that as you're doing this, it's a pain in the butt to write dy dx every time. So we're just going to do it with y prime. Okay. This might not mean much to you. I get it. It will make sense, however, when I take you through this example. Okay. There's one thing you need to remember when doing this, and that is anytime you take the derivative of a y, you need to include a y prime at the end. You need to chain on a y prime. Okay? So it goes something like this. The derivative of y cubed, you treat it just like if it were x cubed, so you would get 3y squared. But again, since I took the derivative of a y term, I have to include a y prime after I'm done. Because that says I took the derivative of y with respect to x, plus the derivative of y squared. The derivative of anything squared is just 2 times that anything, but again, there's a y there, so I have to include a y prime. The derivative of negative 5y would be negative 5, but again, took a derivative with respect to y, so I get a y prime. Let's stop there for a second and check for some understanding. Are you following what's going on here? Okay, now the derivative of x squared is just 2x. And here's where we get a little weird. Okay, so I'm going to stop for a second and get a little philosophical on you. What we saw in the previous slide is that these should actually be dy dx's. So it should look something like this. And I'll finish that up in a second. But that's what we're supposed to do traditionally. But being lazy people like we all are, we change the dy dx's to y primes. Now, the reason I mentioned the stuff in blue is because when we took the derivative of x squared, we got 2x. And we took the derivative of x with respect to x. Okay. When I took the derivative of y cubed, I took the derivative of y cubed with respect to x. The derivative of y with respect to x, etc., etc. So what happens when I take the derivative of x with respect to x? Well, what is dx over dx?
Would it just be 1?
It's just 1, right. So again, being lazy people, we don't bother writing that. From a practical standpoint, what that means is when you take the derivative of an x term, it's just a plain old derivative like you've done all along. Okay, equals the derivative of -4, the derivative of any constant, is 0. Okay, are we good? Give me let's do an emoji thumbs up, just for giggles. See who's paying attention. If not, speak now or forever hold your peace. Cameron, Drew, Yvonne, Yanni, you good? Are we good? Yes? Good? Okay.
Yeah.
Beautiful. All right, get rid of this. If you want to write dy dx, you can. Some people just like doing that. Surprisingly enough, the hard part is next. Most people struggle with the following, and that is, I want to find the derivative, so I have to solve for y prime. Okay? And that's something new for us. We haven't really seen a derivative that has the y inside the derivative. We've always taken functions that were y equals blah, 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 like Bella worked with earlier on, and when we take the derivative, there's no y there, it's y prime. Now through implicit, we all of a sudden have y's in the function. Well, that's okay. Now, instead of just plugging in an x, you may have to plug in an x and a y. All right, questions before we move on? No? Okay, good. Now, what if we take that puppy and we find the second derivative? Okay, so that's what we got for an answer. Now, all of a sudden, notice we have a quotient rule or a product rule. And I wanted to do this for two reasons. Number one, to practice some implicit, but also to help you realize that I could rewrite this that way. And some of you are probably already getting to the point where you don't like the quotient rule, you don't like the product rule, you don't like either one, too bad, or you like them both. So you got to kind of figure out which one you want to use. Marcus, quotient rule or product rule? However, be warned that the product rule has a chain rule wrapped up inside of it. Which one would you prefer?
Quotient rule.
Quotient rule it is. Okay. All right. Y double prime would be equal to the denominator on the bottom squared. Bring the denominator up on, whoops. Bring the denominator up on top. Times the derivative of the numerator minus big honk in parentheses the numerator times the derivative of the denominator. Okay. Well, we did this already. Something similar, I would get 6y, but because I took the derivative with respect to y, I need a y prime on there. Plus, the derivative of 2y is just 2, but again, I took the derivative with respect to y, so I'd have a y prime, and the 5 just goes away to 0. Now, you're saying to yourself, self, that's ugly. What do I do now? Well, this is the part you're not going to like. What are those two puppies equal to?
The value above.
Yep. Hold on, I lied. Let's go 6y squared plus 4y minus 10 minus 12xy times, I'll come back to that in a second, minus 4x, I'll come back to that in a second, all over this monstrosity on the bottom. Very seldomly, I'm just going to say this, do not simplify denominators. Just leave it alone. These parentheses then are what we had for y squared, or sorry, y prime, so this would be that. And you'll notice it's not getting prettier, it's getting uglier. But there's an easy way that we can fix that, which I'll get to in a second. Any questions so far? You see what I've done? Okay. What would be nice in this problem, if instead of just asking for the second derivative, it would have said something like, what is y double prime of 2? Because then I don't have to do any of this simplifying. I could just plug 2 in there ad nauseum and just go crazy on that, plugging in a 2. But here I need to simplify. I don't want a fraction within a fraction. Therefore, I'm running out of room here, but I would multiply the top and the bottom by this. Okay. And it gets ugly. And I'm not going to finish it. I'm just going to stop there. Mainly because I'm running out of room. But again, it gets worse. This is not a very common practice with implicit differentiation. More than likely, you would see something like this, where you would be asked to find a second derivative, but skip the whole simplifying thing. What I wanted you to realize mainly about this second derivative is this idea of taking this business and plugging it in for the y primes in the second derivative. Okay? Now we can combine concepts. So now I'm going to combine a chain rule with an implicit differentiation. And we're going to make it a little bit more straightforward because now I'm going to plug and chug in at a point. Okay. What is the slope of the tangent of the graph? In other words, find the derivative. And in order to find the derivative, I need to plug in 3, 1 when I'm done. All right, so we go. Now notice there's no y prime here because I've got y's mixed in and I don't know how to simplify it. So we'll do the left first. The left would be 6 times the quantity x squared plus y prime or y squared to the first power. I did not take a derivative with respect to y, so there's no y primes added on there yet. But now I need to chain on what's inside. 2x, derivative of x squared, 2x, plus 2y, y prime. Okay, let me stop there for a second. Does everybody follow that derivative on the left-hand side of that equation? We're good? Okay. Chain rule on the left. What's going to happen on the right? And this is something that people forget about all the time. That is a product rule. Because x and y is a product. I don't like to mess around with the 100. I just like to put the 100 out in front and leave it there. It's up to you. Derivative of the first. The derivative of x is 1 times the second, plus the first times the derivative of the second. The derivative of y is 1, but I took a derivative with respect to y, so I need a y prime there. Are we good? Okay. Now, this is what I was talking about in the last one. I could go through and solve for y prime, but I don't care. I'm going to plug and chug instead because I know what x and y are. 6 times 9 plus 1 times 6 plus 2y prime equals 100 times 1 plus 3y prime. Okay, so that's, let's see, that's 1060, 360 plus 120y prime is equal to 100 plus 300y prime. Okay? And now I have to solve for y prime, but I would argue that this solving for y prime is a lot easier than the previous one. 260 is equal to 180y prime, so y prime is equal to 13/9, if I did my math correctly. And I believe I did. Technically speaking, we should do y prime of 3, but that's our value. Questions on that process? Going back to this step, I could have multiplied all that out and solved for y prime so that I have y prime on one side, all the other gunk on the other side. However, again, I would argue that this plug and chug early is an easier method to get my derivative down here. And then again, the problem might say, well, what is the equation of the tangent line? Then you just take that slope, that point, and put it into point slope form, and you're done. Okay, how are we doing so far? Some of you look like your brain's ready to melt, but that's okay. It's good for you. It builds character. Puts hair on your chest. All right, we're done.